Hello. Today we're going to do Quicksort. Okay. So let's build an array. Array of numbers. Quicksort's one of the fastest and most common sorting problems that you'll hear of. It's very easy, and it's very easy to look at, and it's very quick. So you build an array, put a bunch of unsorted numbers in there. All right, that's good enough for now. And then we're going to want to build a recursive method where we divide and conquer. We split the array into half, as close to half as we can, and then we define like an index value, which is the number in the middle that we split the array into two around, and then we recursively try to sort those two array pieces, and we move elements around by defining one element in the array as the pivot number, and we compare everything against it. Everything less than it, we move to one side. Everything greater than equal, we move to the other side, and then we reassemble the array back together. Well, we're actually going to pass the array as a reference, and we're just going to pass pointers or indices, digits that are indices, like this would be 0, this would be 1, 2. We'll just pass the indices around as we work through it. So we're just going to be modifying the array directly, and it'll reference back to main as a sorted array when we're done. So let's create a method called Quicksort, and we will pass it the beginning index and the last index. So we'll send it 0. Actually, first let's put the array as the first parameter. And then we'll pass it 0 for the left, and my array dot length -1 for the right. So the furthest index out that you can modify, right, without getting that index out of bounds error. Let's go ahead and generate that. Make these meaningful, left and right. All right, so let's go ahead and say we're going to stop. It's recursion. We don't want infinite recursion, so we want to stop once we've compared our left pointer, left pointer, left pointer, and right pointer, right pointer. Once they cross, we don't want to keep going. So if left is less than right, then we continue. First, let's identify the index, which is where we split the array, remember. Let's call this partition. If you look on the internet, other quicksort algorithms on Wikipedia and such, they always use partition. So we'll partition based on the same parameters, my array, left and right. Now here we're going to quicksort recursively, and our left will remain the same, but our right is going to be that index, because remember we're splitting it in half. But the middle element we're saying is already sorted, so we'll start with index -1, and on the other side will be index +1. So index +1 is going, or sorry, -1 will be our right-hand side for that run, and then quicksort again on the right-hand side. Since we divided it up, it's going to be index +1, so we're skipping index all the way to the right. All right. Let's generate a partition method, and it actually picked the letters we want, left and right, so we don't have to worry about that. Okay, so let's get a pivot value. Then we will compare the items in this portion of the array against pivot and move if less than, and then we will move the pivot itself into place, and then finally we'll return a new index, which we'll use to split the array again, right? And that's what we're going to do in this method. All right, so pivot value is, well, let's just pick the end. There's a lot of different ways of picking the pivot. Sometimes people take this one and this one add together, take the middle number, and it may have a slight impact, but I've heard that it's very minimal. So let's just take the one on the right, because it's easiest to envision what's going on that way. and it doesn't really affect performance super much. So, or that's not, it doesn't affect performance a lot. Okay, so my array at the right is going to be our new pivot, it's going to be our pivot. All right. Now let's begin our comparison process. I want to define an iterator outside of the loop. Imagine, if you will, having a pointer just to the left of the first index, and the first time that we compare with it, we will move it to the right, so it ends up on the first one just before we do. And the other one we'll start here on the first element of whatever that portion of the array we have, and we'll move it until it compares against the pivot as being less. Then we'll move them both, compare, swap, and move on. So let's do that. So int I equals the left of this particular run minus 1. And then let's do our for loop, and we'll do int j is equal to the left, and we'll go until j is less than or equal to the right, because we're going all the way to the end of this portion of the array. Increment j. Now let's check if the array that we've got here at the position of j, we can't compare against I because that would be potentially outside the bounds of the array at this point, right? So you already know it's j. Good way to remember it. If the position of the array at j is less than the pivot, every comparison is always going to be against the pivot. That's the whole purpose of this, right? Then, now remember I said we got to increment this before we do our first comparison. This is where we increment I. And now we're going to be comparing, and it may not be, you may not be comparing this against this or against this. It may be a couple of times before you find a number that's less than the end, or it may even be the second recursion, because we don't know what order these are going to be in, of course. So if you look at it that way. All right, so if it's less than the pivot, then we will swap them. We'll swap the contents of my array at I with my array at j. Actually, I think it's easier to create a swap method, since we're going to use it twice. That way we don't have to write that code twice. So we'll swap those two items. Let's build the method after we finish with this. All right, so next we're going to move the pivot itself into place. So again, we're going to swap the location of the pivot with, let's see, we're going to swap it with I plus 1. So right where we finished this this situation here, we move to the right one, and that's going to be our new index. So we're going to swap. Oh, sorry. That will be our new index here. So we'll go ahead and swap my array, and it's going to be I plus 1 and the right, because the right is where we got the pivot from. And we'll return I plus 1 as the new index. Let's go ahead and define that swap method now. So swapping, you always have to remember, if you're swapping one position with something else, you put this over here. Well, now when you go to assign this to here, this doesn't exist anymore. So we need a temporary variable. So we'll temp equal to my array at, let's just make that, well, v is fine, I guess. My array at v. And then you could say my array at v, since we've stored that, is going to be my array at r. And then my array at r is going to be temp. And that should be it, but we need a way to now, we do need a way to display these when we're done. So let's go ahead and go back to the main method where we started. And don't forget, we passed this array around as a reference. So all the changes that were made in the partition method were also made in the main method as far as the array is concerned. So let's just make a loop here. For int I equals 0, and we'll go all the way from I to the end of the array here. So do I is less than equal to length minus 1, which will keep us from going outside the bounds of the array. And we'll print to the screen. So we'll do console.writeLine, my array at the position we're looking at, I. And then we'll do a console.readLine to pause for input so you guys can actually see the output. You'll notice there's an error here because we didn't tell it what to step by. Step by 1. Go ahead and hit F5 to run that. And let's compare. So 1, 1, it's like 1, 2, 3, 4, 5. 2, 3, 4, 5. We've got the right number of elements and they all appear to be in order. All right, so that's Quicksort for you guys. Pretty short and sweet. Any questions, let me know. Hope you have a great day. Thank you.